Thank you for inviting me for this award, and I'm very honored to get this award. And before starting my conference, I will try to say something in Japanese. この度 DPRI アワードいただけることをとても光栄に思います。このような名誉に心から感謝しています。日本で特に京都で賞をいただけることは私にとって大変な名誉なのです。I'll just go back to you have seen this image, it's the El Capitan rock face in Yosemite viewed by a thermal camera. I just, before starting the presentation, just to explain how I use different slides. This is the themes I will show you, and the meaning of this slide is like a summary, a synthesis of what I said in the themes, and then you have some new examples, because during this presentation I will try to exemplify several of these new techniques and also what we can get from them. And also the main point will be these themes, the new techniques that improve hazard analysis. You will show very simple example that we get from these new techniques, and also what we can expect to extract and what we can already extract, and then the access to dynamic processes because of this new technology and also analysis. At the end, I will end by human-induced landslide, because this is really also one of the main concerns now, because human-induced landslide are often landslides are triggered or created by human activity. It's a huge problem, and I think that with this we can have an overview of what we have to do in the future about landslide research. Let's start with the new techniques and the improvement we get from these techniques. If you look nearly 20 years ago, we started with a digital elevation model that were 30 meter, around 30 meter grid cell, and now we get in the beginning of the century LiDAR DM, and it started to be available for scientists at that period. And you see the difference between this catchment view. This is a 30 meter, 10 meter was already better, and now with LiDAR DM with 1 meter or less resolution, or higher resolution with the grid size smaller. What is a LiDAR? Just to remind this, it's you have for instance, you can have an airplane with a laser, and the laser sends a beam, and then you count the time with the different return of the reflection. Then you have the ground, you have the canopy, and you have intermediate reflection. And this reflection gives you you have the time, then you have the distance with the velocity of the light. This can be done also on ground-based LiDAR, you will see that. And what we use usually is the last pulse. It can be done also in shallow water. This is called shoal. And now the number of points you get can be more than 1 point per square meter. If you look here, the results, this is the first pulse return. This is, for instance, here, that from the canopy. Then you have the trees, and the right image is simply the last pulse image. It removed everything because you have the full wave of your return, and you analyze this to get this result. And then you have a really nice view of what occur, what are the processes affecting the slope and the river in that case. It also allows us to reanalyze or revisit old theory. For instance, Strahler in the 50s found that if you analyze topography by hand, in that case, this is the slope, you can find distribution that are Gaussian distributed slope angle. Here the slope angle and here the distribution. And he showed that Gaussian distribution can be used. And that, following that idea, using DM, we started in the 20 years ago to analyze 20-meter DM with a grid of 20 meters. This is the slope angle, and this is the frequency. Those are the points observed in that area. And then we decompose this histogram into a Gaussian distribution. And you see that after 50 degrees, this cliff family slope, I will call it like this, is dominant. And then the idea is that most of the rock instability or rock scar, former instability, must be located within this part. And if you look at this area in Switzerland, this area in Switzerland, there is some cliffs there, and then what you can get, it is that this is former, there are the instability that you can observe in the past rock slide, then they are all located more or less above this 50-degree limit. Now if we move to the LiDAR DM, the recent one, then you see that the slope is a bit different, but not so different, with higher slope here, really going up to 85 degrees. And here is the result of the new decomposition. If you go here, you will find two different limits. One is 24 degrees and one is 48 degrees, which is not very different from the other DM. What you see here, the white line is is coming from the 50 degree limit of the slope from the 25 meter. You see that the 1 meter DM gives you more detail, and the 2 meter, DM gives you more detail. It's really you can see in great detail the slope morphology. And what is interesting in that now if you use the 24 degree, you see very well the morphology of the valley where you have the river. Then it's rather powerful to analyze the slope in a very simple way. You can do that very easily. Now, what are the improvements also you get from that new type of DM? It is here a little shade. You see in red the former inventory that has been made by the group of Guzzetti in Italy, and you see that this was made based on aerial photographs, and then this is the new interpretation based on the LiDAR DM, which improved the location and the hazard mapping. Now it is a picture from Chigura-sensei. Here you see that this is the landslide from Shimizu in the Kii Peninsula that occurred during the Typhoon Talas. But what is interesting in the analysis of Professor Chigura, it is that if you look at the DM that has been acquired before the landslide, you will see that the limit can be found here. You can see that it's traced here, the scars, different scars that have been identified. And you see that on the morphology, we can identify where it has moved before. And it's not saying that it is moving now at that when it was acquired, but that this zone was sensitive to landslide, and the demonstration was the occurrence of the landslide later on. And I will not enter in detail in what we developed, but if we can do some analysis, further analysis of the DM by, for instance, using very simple technique that can be used. If you make the delineation of the landslide on the DM, like here, like this previous image, then you can, with a simple procedure I will not explain in detail, to make a first assumption of the failure surface, even if it didn't occur. This is the slope before, and this is the slope after in red. And this was the hypothesis I did 2 years ago without knowing exactly how it occurred, because just having the DM, and then with a bit more of information, I was able to get this line automatically in a few seconds. And then you see that it's rather good. And then it's, we can develop a lot of tools to use those data, because there is a lot of information that we can use from, get from from such data. I will not enter in detail about what you can do on the modeling. It will be a conference in itself, but I will just show you what are the improvement of these type of data. For instance, here you have simulation. It's a new PhD student working with us coming from Quebec. It's in Quebec, a slope, a rock face, with here you see also the trees. They are not taken into account in the simulation, but this is the rockfall simulation. But you see that you have a great detail. These are blocks, and then you can see that it will interact with the rockfall activity, and it will probably, in some case, make the hazard zone smaller than with previous data. Another very important advance those last 20 years, it was discovered by Vassonnet in France, or in US, but it's a French, who start to work with the differential INSAR, which is the synthetic aperture radar from satellite. If you compare radar image, then you can have a look to the displacement. And this displacement is not, as for the LiDAR, the time of propagation of the wave. It is the difference in phase. Then you can have the half of this distance can be evaluated if between two images, two acquisition, you have less than the half of this distance, you can evaluate the deformation. Here you have an example coming from Norway, where they have a lot of problem of huge landslide, rock slide. And this is, you see, the movement downward, negative, from the direction of the satellite. It's always only in the direction of the line of sight. And this is in the northern Norway. You have several slope moving down. And it's really important in Norway. Why? Because if you have those landslides falling, it creates tsunamis within fjords. And then this is one of the instability, the Nordness instability, and you see that it's well monitored, it's moving down. And what we can see is that if you look carefully, then you have a nice image of the movement deduced by these INSAR techniques. You have the movement also here. This is millimeter per year. And what you can also put on the landslide is permanent scatter, which is permanent target that give you very precise movement. And if you project the displacement along the line of sight, here you have the date, and here you have the millimeter in the direction of the satellite. The movement, you have the blue dots, which are the GPS data, and this is from the permanent scatter target. And then you see that there is a fantastic match between data. And this is really now a powerful tool. The only problem is that Norway is very well, very good place, because there is not so much trees and vegetation. Working with vegetation is a problem with this method. Okay, then for summarizing this first chapter, I will say that it helps us for detail mapping, for movement detection, and also to characterize landslide limit with inventory. And this gives us also new input data for processing new models. What are the challenges? The developments of new tools to extract all the information of this nice data, because we don't extract all the information. We have not yet developed all the tools that can really take everything into account. And this again, the next step is all these data are very difficult to integrate in modeling, because when you model, if you use all this data, it will be really time-consuming, and this is a challenge also. Now I will just show you some more step further, just showing that we can also analyze things in other ways. This is again another landslide that occurred during the Talas typhoon in the Key Mountain. This is the Akatani landslide, and it's a rather large one, but it's controlled by fault, and Professor Chigira has analyzed this. On my side, I tried to do it simply by not knowing several things, but working with blinded work. And I use this Koltop principle. What we develop, it is that you know the slope analysis, which is the slope angle. Then you will get, if you have a topography like this, you will get colors like this. And if you look at the slope aspect, which is the direction, then this is two different maps. But we can join them in one color scheme, which is here the HSI color scheme projected on a half sphere. And then you see the normal in this direction will have this color, and this direction will have this color. Then if you show the topography with that, you will see the different orientation that goes there that shows some structures, or in red other structure, in yellow also. Sometimes it's also only geomorphological effect, just some erosion effect, but usually you can get really nicely the major fault. This is the scar of this Akatani landslide, and if you look here, it's a bit too red, but you can see the different structure. You see this is the field, and you have some surface of fault in that area. And this is very useful because you can analyze very quickly, and then the field work, when you have those data, start to be different. You will work more precisely. Another example, just for the image, this is a bridge viewed with this scheme, and then there is some overhang above here. A train is passing through, it's in Switzerland, and you have also some, you see this surface is one color, this surface is a family of fractures, and so on. You have different structure in that image. Now we will move to how we can analyze failure surface. Maybe you know about Oakness landslide. This is a movie. This is a movie about this landslide that has been done in Norway. This is a very famous place in Norway. This is Geiranger, where it can occur, a tsunami can occur because of this landslide. This landslide is an Oakness landslide in Norway, and this is the viewpoint of the landslide falling in the fjord. Why they are concerned by this such problem in Norway? It is that in 1934, 1 million cubic meter rock slide fell in a fjord and killed around 30 people in Tafjord. And also they have learned in 1905, 1936, they had also tsunamis. And this is different from other landslides, because if it fell in the fjord, then you will have effect not only below the landslide, but all over the fjord. This landslide is rather famous. We had 2 weeks ago a meeting about the possibility to do a tunnel below to do a drainage to avoid the movement. This is the LiDAR DM hillshade. You can see the limits. There is a fold, and then a back scar here. And all this mass is moving down. And you had already some important small volume, not so small, but landslide on the western part here. And the question was how to find, there are some boreholes in that area and in the top, but how to create a failure surface. We don't know, we have only boreholes. And then the idea is to look at the slope just 1 or 2 kilometers away from that area. And then we tried to, one of my PhD students worked on that and make some profile to try to characterize the failure surface. Why? Because we had electrical profile, which is an image of the ground by geophysics, that gives us some information about the location of conductive zone, where you have water, and non-conductive zone. And then, if you look, we were thinking that it's not rounded because this is the effect of interpretation of geophysics, but it's by step, like this. And we wanted to find how works this step. And 1 kilometer further, yeah, it's going, we were able to analyze this. Sorry, I mixed. We were able to analyze this with Coltop. This is the surface. You see there are fractures here, and then if you click on the image, it gives you directly the direction. And then you can make a statistics. This is a projection of the normal to the topography on, if you want, on a map, a spherical projection. And then this is the direction you get here. And then what did the PhD student? He looked at the spacing between the different sliding surface here, and in that direction, this direction and that direction, in order to be able to make some fitting of distribution. You see exponential negative distribution for the trace length and spacing. And also he did that for the orientation, with distribution of the orientation, and then generate profile that are simulation of potential sliding surface. And then you see that there are some realization here, not all, just showing that it's compatible with the borehole data. You can see here these lines here. And what is interesting is that this simulation gave us, if you look at the profile and where they go out from the topography, 70% of the simulation are going out before the toe of the landslide, meaning that it is really highly probable that there was a landslide, which is good to know, but also that it can be used to make simulation, several simulations to see the stability. I will just move, this was rock slide, and if we go toward soil landslide, then it's a small landslide. It's a human-induced landslide because it was reprofiling slope close to a river. And then we observed with ground-based LiDAR, giving the topography, we observe how the topography changed. And if you have this landslide here, and then you see it just rotate, and we analyze the rotation. This is the sliding surface, this is the pre-failure surface, and this is the post-failure surface. Then what you can do is to fit a line here and fit a line here, and look at the angle. And the angle gives you the rotation. And if you have the rotation, then you have the center also, and you can, because you have the scar here, and then you can trace the real failure surface, the surface that is estimated based on a very simple rule. And it demonstrates that rotational landslide are, for small area, are really circular. And we did the same with the scar, fitting on this area, on the scar, fitting sphere, and we obtained really the same radius, 2.5 meter Here it was 2.7.2 meter. And this is the small formula the simple formula to calculate that. And this is really efficient to analyze. And this is the way we can start to analyze, to demonstrate former hypotheses using this new data. Now I will move to another example, which is the monitoring of Eiger. Eiger is a very famous mountain, and on the flank of this mountain, in 2006, part of the mountain was falling down. And it was really important because there were a lot of journalists there. My PhD student had a lot of interviews on TV because that year, on a highway in Switzerland, 2 German tourists were killed by rockfall. And then it was very sensitive. And if you look at this, this is a view of a LiDAR survey. In front, we were just monitoring from there to there. You have this movement. This rock mass was going down here and moving toward us. And there were some specific part here. And this is all the blocks that were moving. You see this also going away from our position. And what occurred is, in that place, if you look carefully, it's difficult, but the movement, there were some precursory movement, and up to 2 meters before, 2 meters in 24 hours, and you see that we were able to forecast the rock fall in that area. At the end, all this instability fall down completely. But what was interesting, it was to see the movement. You see, this is the different epoch of the movement. You see, here is the scale, 100 meters, and then you see the advance of this rock face toward over a glacier. This is the deposit, and one part was moving down here. This is the basal failure. This is the back crack. And 2 wedges were formed. One was going down, and the other was going out. And you see more detail here of the different epoch we monitored. And then what was interesting, it is that if you look at the failure, this is a representation of the direction of the different fracture that you find in the rock mass. There is one which is vertical. This one is going down there. This is like a circle. It's like an intersection of a plane with a sphere. And this is going down, and this is a vertical one. And this is the movement, the vector of the movement in 3D, projected on this plane. And then you see that the intersection of both structures give the direction of movement. It is the same for the downward movement and for the upper wedge that was going down. This is simply the movement total displacement. You see at the end it was 40 meters. And acceleration, deceleration, and reacceleration. And this shows that it's very powerful to understand the mechanism. Another thing which is really important for the hazard, it is that this is cliff above Grenoble. One of my PhD students is working on that and looking at the rockfall analysis. This is, you see, Grenoble is really down there. And you have rockfall, frequent rockfall. This is in 3 years, you have more than 250 rockfalls, and this is the location of the rockfall in the cliff. And what is interesting in that case is that you have the volume, and you can make a statistic of the different rock, the distribution of volume, the statistic of the volume. And it follows power law nearly perfectly. This is the volume, and this is the number of rockfall. And you see this is the exponent, traditional exponent, volume, and this is the frequency for 2 different cliffs. The issue with that, it is really interesting because you can extrapolate what will be you are not observing, which is the larger landslide, the larger rock slide and rockfall. down to this. In this area, there were some rock slide historically that occurred with more than 1 or 2 million cubic meter. The problem is that we have an exponent that is a bit smaller, and then it's probably we have to analyze what will be the relationship between the duration of the inventory. Because longer is the inventory, more you will get larger event. To summarize this, it is that waiting frequency, for instance, the last slide we had, shows that there is a potential, if we can analyze the different volume, for making a statistics between volume and frequency, frequency magnitude, and susceptibility to hazard. This is a really great, it can be a potentially great improvement for risk analysis. Then you have the 3D discontinuity analysis, kinematic analysis, as we have seen, the failure forecast, and another thing is to try to extract data to get the failure surface. What are the challenges, in my opinion, is that we need to have the development of conceptual model to integrate all type of data, because there is not only the data I showed you, but there is also a lot of data that are coming from geotechnical point of view, new permanent monitoring that has to be analyzed. And everything must be set in the same model, and we need a conceptual model. We need also to develop more tools to use such for such analysis. And also, it's mandatory to be able to transfer this knowledge within hazard level quantification for risk analysis. Now we will go to the dynamic process. I just looked at the time. It is, yeah, I have 20 minutes, yeah. The dynamic of the process, what we can get with these new techniques. The first thing is using LiDAR. Here we are in France, near Grenoble. This is a quite famous rock slide in Seychelles. This is famous because here there was a village, 400 people were removed, and it gives a famous law, Barnier, in France, where it was 400 people and the village was destroyed, and after they create a new law about hazard, risk, natural risk in France. We monitor that with a ground-based LiDAR. This is every 10 minutes we have a topography, a new topography of this place. And the PhD student that work in Canada came to us for 1 year, and he started to monitor one zone. And you see this block. This is the date during 2 months. And you see the difference. This is the movement, if you want. The point A, point B, point C, and point T. There is no displacement. But it shows clearly that the point A is moving more in the direction than the point C, in the direction of the LiDAR. It shows clearly a toppling, a movement like this. Okay, this again gives us the indication of the mechanism, and also it failed at the end. Now, another point that is a recent finding by one of our former master students. Now she's working in the north of Norway for a PhD. She's doing a PhD work here in Tromsø. And this is, in this area in Norway, we have every year a slope movement that is monitored permanently because they are closing the road below often. And what we will see is that they were observing the monitoring, and then we were interpreting data. This is the Mannen rock slide moving here very quickly, and there were two different ground-based radar, not by satellite, but on the ground. And this is two point of view. And we were looking at this rock face in this area, And this is the LiDAR DM. You can see that is rock face. And these rock face are, you can see here above you have lake. It's important, small lake. And this is, you see, instability that are quite active. But what was observed first, it is that in August 11, this part was moving down. This is the distance to the LiDAR, to the radar, and then it was going back. And in that case, next year we saw in 12, before in June, that this moving was going out. And then this was confirmed by radar satellite INSAR that you see again. This means that the rock slope is inflating and deflating, and you see during the summer doing this. And this is some point with that are shown here. This is some point the displacement with the ground-based INSAR data showing the same. And what happened? You see here, this is the rock face that was moving. This is an image of the movement by the data projected, the radar data projected on the DM. And you can see a detail of the rock face. It's really rock, but above what you can see, water going inside the mountain. And what happened, it is that when the fractures are filled by water, then this part is going out. And then when it's in July, August, when the frozen part disappears, then the water evacuates. And then the rock face goes down. This means that this is a process of fatigue. It means that with time you have the rock face that is changing movement by movement, and then it will create sort of hysteresis and degrading the material. And another topic recently developed, it is the thermal effect on rock face. This is a flake in Yosemite, where we are working with Collins and Stock, who is the geologist of the park. And they have shown recently that there is movement by 1 centimeter of this flake with the thermal change. If it heats, then the space between this and the flake increase and decrease in the night. And you see that there is a trend slowly with months that this displacement increase, the maximum displacement increase. We observed that for one night, for 24 hours, using crack meter and thermal resistance to monitor. And what we see, this is the crack meter we used. This is the thermal view. You can see here, this is in the morning, the flake is cold because during the night it cooled. And this is the difference between different periods. You see here, from the night to the morning, you see that this part was cooling, negative. In the day, between 8 to 11, this part was heating by 20 degrees. And this is also the other period. Now, if we look at the temperature, this we have also thermal resistance, and you can see the different point, and you see how it changed in temperature during the night, cooling, warming in the day. This is extracted from the same point from the thermal image, temperature, time. And this is the real temperature the air temperature. You see that there is an effect. It's not exactly the same temperature because they are radiation. And if you look here, this is the LiDAR information. This is around half a centimeter to 1 centimeter deformation. It means that the flake went toward us during the day by 1 centimeter, and then disappeared during the night. And you have the movement, again, of different place, contraction during the night, expansion during the day. And the explanation made by Collins and Stock, who published a paper in Nature Geoscience, that it is going, the flake is doing like this, and then the cracks increase in that area. I will just show this very quickly, but because I have only 10 minutes to end. But this is just to show one thing that has not developed with surface process analysis, but with geophysics. We have a landslide where we work close to our university, 1 hour from our university, and this landslide is monitored with the University of Grenoble, who worked on that. And it's interesting that it is passive seismic, the analysis of seismic noise made by the car, the birds, the tree, the wind. And then they developed a method that is very similar to the seismic one, to apply to earthquake. It is to look at the change in velocity of the surface wave. And I will just show that because Professor Wong can be interested here about this. It is that it slides here, and in 2000 we were monitoring that, and the bottom of this landslide moved in 2010. And what we observed on the data, this is the situation just after the landslide, and what we observed, this is the velocity, surface velocity, and you see this is the shear wave velocity at the surface, and we see clearly before the collapse, a change a few days before, and then 5 days before, a drop in the velocity of this surface wave, which was just before the collapse. And this shows that there is probably fluidization of the material. My colleague showed that by simple simulation that we expect a zone that was weakened at between 9 and 11 meter depths. And this is because this is the fit of a deformation profile. We have the borehole up to here. And then this part was really deformed. And we can expect that the deformation plus water fluidized the material. Then we have seen that it's interesting. All these results are interesting for analyzing the movement. We get also, it's easy now to have a permanent monitoring with the computer availability. And it gives us access to physical property, because you can deduce by model the physical properties. It's a challenge, because now one of the things is the evolution with time of rock mass, the property of rock mass, and what is the fatigue process. We will go more toward more fundamental physical processes, and also to analyze, it must be known that when we have a more detailed view of the processes, they are more complicated. Now to end, I will just show you a few examples of human-induced landslide, because human-induced landslide is one of the major topics, one of the major sources of landslide. It has been developed by Terzaghi already in his classification. You have here some example of this classification he did in 1950. But if you look at some statistics, human-induced landslide can reach, you see, from 30% to 80% of the landslide can be triggered or favored by human activity. Switzerland is a bias because, in fact, it was not all landslides were not informed about the source, human sources. But you see, the statistic is rather impressive. It's one of the major common, most common type of landslide contributing factor. If you look at what it has been seen in New Zealand, unsupported cut slope, 57%, poor water management, engineering retaining structure that are not well designed. In Switzerland, in around 200 landslide, it's existing embankment that are failing. The land use change generate landslide, or water deviation that are creating landslide. This is really the 7 class we deduced: slope reprofiling, groundwater flow perturbation and fast pore pressure change, surface water overland flow modification, land use change and land degradation, inappropriate artificial structure, vibration and explosive, and aging and degradation degradation of infrastructure. We will go to slope reprofiling. The first one, it's historical important because in Switzerland we had this landslide in 1889, which killed 115 people. This is the rock avalanche of Elm, described by Heim, which is a famous Swiss geologist, one of the father of the landslide research. And why it was triggered? 10 million cubic meters were triggered because there was a quarry at the bottom of the slope. And this moved down up to 300 kilometers and going there up to this place. This was the first rock avalanche description. The groundwater perturbation, pressure change. Here we monitored, and this is the link between the new techniques and the human-induced landslide. In this area there is a lake and a dam, and you can see that this is a vegetated landslide. You see, this is very difficult to monitor. And you see this spot, I will explain to you what it is. And this is when they draw down, they just empty the dam for maintenance, and then landslide occur here, it's activating a landslide. And what we did is that first, this is the cross-section of the landslide, doing like this. This is the water table, the water level of the lake. And this is the target we used. And what was the target? We used the LiDAR, and the LiDAR with big target that are like big expand polystyrene cubes or sphere, we put on the landslide here. And then, monitoring that, we were able to follow this target, but several targets were there. And using this LiDAR, without doing a lot of real complicated investigation, we were able to see the different target movement here, the total displacement up to 60 centimeter displacement. And you see that this is the level of the lake, and you see clearly the effect of the well-known drawdown process. When you empty the lake, the process accelerates. And this is the movement of the different target. Another problem is the aging of infrastructure within slope. Here, this is an example of small earth flow, but it was triggered by, you see, this is a pipe, and it was triggered by a hole in the pipe. It means that what happened when you have a aging of infrastructure? It means that this landslide was triggered by a 3 years return period precipitation, which is not very high. But adding the water in the soil plus the pipe leaking makes it now sensitive. We had exactly a similar scenario killing 3 people in 2002 in Switzerland. This is just a field for the cows, and it was just triggering a 4,000 cubic meter, or now 2,500 cubic meter earth flow, and killed people just below. Then this is one of the challenge also. And surface flow modification. This example is a bit funny. because this is an example made by Zezer in Portugal. They tried to protect a soccer field. Then they diverted the river because it was activating the landslide. But what they didn't thought, it was the next meander. Then the river starts to erode this part and it creates a second landslide. Then it's why it's really important, and my message it's really important that we have to look at the landslide in their environment, but the changing environment, which is really important. What we have seen also is that if we statistically, we have done some statistical analysis and simulation over Switzerland during comparing the event to 2005, making 5,000 landslides. What we discover is that if we create landslide, simulation of landslide stochastically, then we have less landslides simulated in the urban area, which means that in urban or inhabited area, and then it shows that clearly they are an effect of human activity. And to end, this is an example from Venezuela, where you can see that the impact of new techniques will have helped a lot. This is an area where they created a viaduct for a highway near Caracas. And this is from a landslide that was possible to detect. But we had no movement and no real detailed map. And this is the highway, and this is the zone. What happened? This is, again, environment has changed. You see, this was empty, now a lot of houses. And you know that water pipes are leaking everywhere. And then you can expect that these reactivated the landslide. And it shows that this was moving down, probably because of this part. And you can monitor that. You had two important things. One thing, it was, if we had the LiDAR DM, we were able to map really in detail this, the landslide, former landslide. And second, with the INSAR, it was possible to see the movement of the houses and to map really in detail the movement. What occurred in 2006, it is that this was the protection, but not sufficient. You see the bridge was closed, and this was arching here, and this is a few days later. The bridge broke. And this is a really example, a really good example of what can be, what is really important is to look at the environment. Just one thing, it is a landslide. This I forget that I had this last example. It's a landslide in Norway, in Quickleys. In Quickleys, what you have, it is that there were 10 houses here, and this landslide occurred in the morning. Fortunately, only one woman with her child was there, and they were safe. And this is the houses moving down on Quickleys. And what happened? In that case, these landslide Quicklay are very sensitive. This zone was not mapped really, even if they have a huge program in Norway for that. And we visited this area. This is the rock below these Quicklays, the clays that are very sensitive. And then they blast this zone. This is a cross-section of this area. They blast this zone to create a new road. And then it pushed down a block and trigger a landslide. If I come back here, this was the work here, and the landslide created was over there. And then you see that again, we have to look at the full environment of landslide, which is really important. This is the frontal part. I think that to conclude, there are three main issues that are linked with time. First is to understand how the geotechnical properties will evolve. The degradation, as we have seen, we can look at least the effect of the degradation. There are things also that the aging of infrastructure are really important in the management of the landslide. and also the change related to slope modification. This is, I mean, slope environment. Then landslide must be viewed in their environment. Here, I will not read the 7 point, but we conclude our study about human-induced landslide by promoting 7 recommendations, going from modification of did the slope modification affect the stability, but there is surface water is really important. We change the surface water flow. Degradation process. Is there some degradation process? Are artificial structure taking into account in the full environment, not only just around, but looking at what can occur? And this is really important. In conclusion, the emerging techniques allow us to access the surface processes in almost real time with a great accuracy. This is, if it's associated with new tools, this will help us to understand better the process of landsliding. It's because we are going now toward physical processes, because we, as you have seen, rock changes. You are also with geophysical monitoring, we can get some more physical process. But one of the problem is that if we have more detail, the nature becomes more complicated, and then it's a challenge too. And then it's important to understand this, because now, as you know, the change of our land planning, land occupation is very fast. And then it's really important to be able to follow this change. And these new techniques give us a way to analyze this. I will thank all my co-authors that are PhD students and colleagues, and also I will thank very much Chigira Sensei for his help, and welcome I was welcomed by him in 2015. And also I will say that I consider that Professor Chigira is the scientist who identified the slope tectonics process, and that's why he's organizing next October the Slope Tectonic Conference we initiated in Lausanne in 2008. Thank you very much, and ご清聴ありがとうございました。